issues that we'll get into a little later with the chiller plant. We reviewed the BAS with the facilities staff to kind of gain an understanding of the control strategies being used in the building and build an understanding of how the systems operate. And very importantly, we set up a lot of trending. Good trends are the best way to baseline a building's operation, so at least you can capture that for later use. And it's also a requirement for the utilities retrocommissioning program. So good trends up front. So just kind of going into the kind of building we were looking at, 675,000 square foot, 25-floor medical office building. That's part of a larger hospital campus. The building has a small 12,000 square foot data center. And the data center is served by some Liebert units that sit in the space, and those units are fed chilled water from the chilled water plant. An entire floor of the building is dedicated to MRIs and CT machines, and those units also utilize chilled water for their process load. Another important fact about the building is that it's an electric-only building, so there's no gas service to the building. Meaning all of the heating is done with electric. So while interviewing the facility staff, we kind of learned about some fairly major operational issues that they were experiencing. We learned that the chilled water plant was frequently tripping out on low temperature alarms. This building in particular utilizes a series counterflow configuration for a few of the chillers in their plant. And so with a low delta T issue in the building as well, they were having a lot of low temperature trips on their chiller plant. Because of this, the MRIs on the third floor of the building were losing images, and so when this would happen, they would lose a lot of the big revenue generators in the building. So MRIs and CTs are big revenue generators. And they were losing images. So, you know, unhappy tenant when that happens. They also had manual chiller staging as part of the plant programming. So on days when there would be big outside air temperature swings, they would experience issues. So they have a small facility staff. They're not able to sit there and babysit the front end all day. So they would do one of two things. They would false load the chiller, because we did discover that this plant was fairly oversized for part load operation. So they would false load the plant in order to keep it running when they knew the outside air temp was going to rise that day. Or they would just, you know, go about their daily maintenance tasks, and they would wait for pages that they had set up. So they'd have a pager, they'd get an alarm, and they'd have about 15 minutes to get back to the plant and get a chiller up and running before that MRI loop would rise above its tolerance levels. So that's, you know, both are bad. So we're either false loading the chiller or we're waiting for alarms and trying to race back and get another chiller going. So there was also some programming issues involved. This plant was not commissioned when it was installed in 2008. So there really wasn't any quality control on the original programming, and they also had their control service provider come in and try to fix the programming to no success on that either. So they're kind of in a pickle there with the chilled water plant. Another issue for them was that they're using a tritium-based Niagara BAS, which is an open source contractor level control system, while the remainder of the campus is using Johnson Controls Metasys as their front-end software. So let's just jump into some of the building systems. The chiller plant in this building is located in the penthouse. The plant consists of 5 York centrifugal chillers, 3 of which are 800 tons and 2 of which are 400 tons. If you can kind of look on this flow diagram. Chillers 3 and 5, if you look, are piped in a series counterflow configuration, which means that the chilled water here enters chiller 3 before going on to chiller 5, and the condenser water enters chiller 5 before flowing into chiller 3. So there's a counterflow configuration there. These series counterflow chillers are then headered in parallel with the remaining 3 chillers. They also have a plate and frame heat exchanger for waterside economizer mode used in the winter. They have variable primary chilled water distribution, and these pumps are designed to be 1 pump per 800-ton chiller. So 1 pump per 800-ton chiller, or 1 pump per chillers 3 and 5 operating in series counterflow. On the condenser water side, there's 3 variable speed summer towers sized to operate 1 per 800-ton chiller. And there's 2 variable speed winter towers, which are equipped with basin heaters. And these winter towers are programmed with a de-icing mode for use in the winter. So you might ask, why series counterflow? Well, a big reason is efficiency gains. So on this efficiency curve here, you can see the y-axis is kW per ton, while the x-axis is percent load. And our upper curve here is the efficiency curve at 85-degree condenser water. And you can see that series counterflow is fairly significantly more efficient than the 800-ton chillers themselves. It's also good to note that operated individually, chillers 3 and 5, which are the series counterflow chillers, have a efficiency curve that's similar to the 800-ton chillers. So here's just some actual pictures of the plant itself. On the upper left here, you can see the chillers all in a row, and a little bit out of the frame here on the left is the plate and frame heat exchanger. And then in the bottom right, you can see the condenser water pumps on the left and the chilled water pumps on the right.
And Mark, am I unmuted? Can you guys hear me?
We can hear you.
Hey, there we go. Good. I got through some technical difficulties there. It took a while. But one of the comments just to make on this plant is that a lot of times they would be running, and the engineer who had designed it said, run the series counterflow machines as your lead because that's the normal, most efficient way to operate. And we concur with that. The struggle is a lot of times in part load conditions, this building would run sufficiently with only one of the 400-ton machines in operation, and the second, series counterflow machine would be trying to run because it's enabled, it's calling to run, but the unit would end up basically short cycling out on low temperature because the load wasn't there to sustain it. And that's what Mark was talking about false loading. And the problem with that is that once it basically shut down, you would have a low oil temp, and there's just a time lag before that machine can just restart itself. So if they were sitting at that 400-ton mark, somewhere in there, or the 350-ton mark, really, the first machine was doing the lion's share of the work. The second machine wasn't loaded up enough. So in many, many hours of the year, that's sort of the situation. And the problem would be with sort of the second machine would lock itself out. They'd need to get a little bit more cooling, and the second machine wouldn't end up coming on. It would have locked itself out, or it's in some reset and hasn't started, so now you're starting to get a little warmer temperatures. So they were just sort of having troubles with that, right at that sort of load point that they spend a lot of the year at that load point.
Okay, thank you, John. That is good background. So I mean, basically the overall issue is that they don't have a chiller that they can run at part loads without false loading it. That's really the issue here. So we'll kind of talk about what happened, what we did to improve that operation there. So up on the screen here, we have an example of the Niagara BAS graphics. This is one of the 4 main building air handlers. The air handlers are located in the penthouse, which is the 25th floor of the building. These air handlers there's 4 identical 125,000 CFM air handlers, each with a 250 horsepower supply fan and a 100 horsepower return fan. Each supply fan is controlled to its own down duct static pressure sensor. So each unit is controlled to a separate static pressure sensor. These units have chilled water cooling only, no heat. So the way they handle that is they raise the supply air temperature set point and allow the electric reheats at the VAV boxes to handle any reheating that's needed. And they do have cooling only boxes, so they do have to keep that discharge air temperature fairly high so you're not freezing people out. These units serve individual risers that feed medium pressure duct on floors 2 through 24. Each floor has a ring of ductwork that's fed from each air handler. So essentially these units are headered together at the floor level, which is important, and we'll kind of discuss that a little later. So these are the heat exchangers located on the 3rd floor of the building. These provide both a pressure break and a separation between the chilled water side and the processed water loops. 2 heat exchangers, heat exchanger 3.2 at the top here, and heat exchanger 3.3 operate in duty, and the middle heat exchanger here, 3.1, operates as a standby, and the way it's piped, it can serve either the data loop on the bottom or the MRI CT loop on the top. The process loop pumps here and here are controlled to a loop differential pressure set point, and motorized valves on the chilled water side of the heat exchangers here and here modulate to maintain a process loop supply temperature here and here. So kind of just jumping into the retro commissioning project itself, what you're looking at right now is the Niagara graphic of the chilled water plant, and just some fairly obvious issues just right off the bat that you can see in this picture here. We've got excessive chilled water pumping. So if you remember, these pumps, these primary chilled water pumps, are designed to run 1 pump per 800-ton chiller. So right now we're running 800 tons in series counterflow here with chillers 5 and 3, and we're running 2 pumps at 100%. You'll also notice that our 3rd floor differential pressure set point is 10 psi, and we are unable to meet it with 2 pumps at 100%. You'll also notice here that we're running low delta T here. We're running about 7 or 8 degrees between supply and return. So that's a fairly common problem, but in this situation, it's exacerbating the part load operation on the series counterflow chillers. So at the bottom here, you'll see the design delta T is 16 degrees, and like I said, we're running between 7 and 8 delta T from supply to return, and you'll notice our flow here is 1600. So at these parameters, we're at about 500 tons on the plant. So also at these parameters, if we were at our design delta T, we would only be running 750 GPM, which is much less than 1 pump, because these pumps are sized at around 1600 GPM. So some issues with the air handler, like we discussed earlier, what the facility staff is doing here is they're locking out the economizer mode. So the outside air temp here is 45.5 degrees. Our economizer lockout set point is set below that, so we're not economizing here. We're using mechanical cooling. which is operating fine for them. They're meeting their set point, but they are adding unnecessary load to their chiller plant, but they're doing it on purpose to keep those chillers operating. You'll also notice here that they've basically set themselves up for a situation where they could be without cooling completely. If the outside air temp drops to be between 43 degrees and 45 degrees, they have no cooling. They've locked out their chilled water valve, and they've also locked out their economizer mode here. You'll also notice that the fan speed here is at 100%, which always raises a flag. This is a variable speed system, and the fan's at 100%. And if you look at the other air handlers that are headered together with this unit, you'll see that air handlers 1 and 2 typically operate at 100%, while 3 and 4 are operating at a lower speed, typically 60%. So there is some fighting going on there, and what's happening is that fans 1 and 2 are operating faster than they should, while 3 and 4 are operating slower than they should. Like I said, this is a VAV system, but we're not using, we don't have static pressure reset programmed in the system here. So they're kind of missing out on an opportunity there. So these are the measures that we came up with our initial pass. So these are our energy savings measures as part of the retro commissioning project. Our target for this project was 800,000 kilowatt hours. So step 1 is RCM 8 here. We want to reprogram our chiller plant so that we can attempt to solve our operational issues first. That's the first and foremost thing that we wanted to do. And as part of that, RCM 5 here, we want to bypass chiller 3, which is one of the series counterflow chillers, and only operate chiller 5. So that would be, we would operate a 400-ton chiller as our first stage of mechanical cooling and have much better part load control. Once we fix the issues with the plant, we can then implement RCM 1, which is economizer optimization, which is basically just a set point change. We can raise the economizer lockout set point on the air handlers to be between 65 to 68 degrees and stop false loading our chiller plant. We can also correct the air handler fan speed control. So the idea behind measure number 4 here is that we would control all of the penthouse air handlers to the same fan speed command, and we would modulate them to control to the worst case down duct static pressure sensor. And that way they would, since they're headered together, they would all operate at the same speed. And you'd get better operation out of those units. With the fan speed corrected, we could now effectively implement static pressure reset out in the building. And we typically do this by polling the VAV box damper positions and trying to reset the supply static pressure based on demand. Many of the tenant spaces are only occupied between 6 a.m. and 8 p.m., so we recommended a nighttime setback at the VAV box level. Airflow set points and temperature set points were modified for unoccupied mode. So important for this building is there's some cooling only boxes, so we're okay to set the minimum airflow set points on those in unoccupied mode to 0 CFM. But it's important to note that this building has electric reheats on the VAV boxes. So when you have electric reheats, you have to be cognizant of your minimum airflow that's required for those reheats to operate properly. So that's just something to keep in mind if this is a measure that you're recommending. So since our most pressing issue to solve on our chiller plant was our chiller plant, what are our options here? So we could modify our existing Niagara BAS programming. That would be option 1. We could keep the Niagara BAS, but gut the programming and start from scratch. But that doesn't solve the problem that we would still not have the campus standard as our front end. So a third option is to upgrade the chiller plant controllers to Johnson Controls NAE controllers and then reprogram the entire chilled water plant. So the owner opted to actually go forward with a chiller plant controls upgrade, which pretty significantly modified our retro commissioning scope. So it kind of went from a retro commissioning project to a chiller plant controls upgrade. And we were tasked with providing completely new sequences of operation for the plant, as well as some functional testing on the back end. So some of our goals for this controls plant upgrade was obviously system reliability. That was the big issue. We want to get rid of these random shutdowns. And another big benefit to this was automatic chiller staging. So prior to this, the facility staff would have to manually stage the chillers up and down. With automatic chiller staging, they would have to act to prevent chiller staging up and down. So this is much better for a facility staff that's not sitting in front of the BAS all day long. By doing an upgrade, our BAS would be in line with the campus standard. By improving the chilled water plant operation, we eliminate MRI imaging losses and increase the tenant satisfaction. And we also made an attempt to standardize plant control sequences across the hospital campus. This hospital has several chilled water plants on their campus, and where possible, we tried to standardize the sequences. A good example of this is the de-icing mode on the cooling towers. We basically just pulled that identical sequence from an existing chiller plant and just plugged it into this plant. That helps the facilities staff with the operations because they know what to expect across their campus, and it's a big benefit for them. We were also hoping to get increased savings over and above our retro commissioning project, our original expectations for the retro commissioning project, and by upgrading the controls, we would have a better level of control there. And big for the owner as well as the utility is persistence of the measures. In the current configuration, they had to do a lot of overriding. Whatever you can do to eliminate that is always a benefit. So some challenges here. Increased cost to the owner. They went into this project not thinking that they would be taking on a big financial burden here, but it's good to get work on owner buy-in, make them aware of the timeline of the project and the potential problems, and make them aware of the benefits too. There's a lot of benefits to doing this controls upgrade, so make them aware of that. Most important is coordination. So when you do go forward with a project of this nature, there's no general contractor. This work is direct to the owner. So you have to be cognizant of upfront of who is taking care of what portions of the work. Someone should be the coordinator here, and it ends up typically being the retro commissioning service provider, us. So it's up to us to kind of direct the work. Who's up to bat? Whose turn is it to start making some moves and making things happen? And it's important to stay on top of it because things can pretty quickly fall off people's radar. So here's a screenshot of the new Johnson Controls BAS graphics. After the plant controls upgrade and some functional testing was complete, we had a lot of positive results. During functional testing, we were able to track down the source of the excess chilled water flow. We found an abandoned control valve between the plant and the air handlers that was originally used for flow control. So originally the plant had constant speed pumps, and this valve was intended to modulate to meet the flow out in the system. So this valve was never demoed. It was just left in place, and eventually it failed and was just allowing a lot of flow to bypass directly back to the chiller plant. And that's why you can see now that we've isolated that valve, we're able to meet our differential pressure set point on the third floor here, and we're able to do it with one pump at part speed.
And I think what Mark just said is really important. I mean, part of this presentation is to kind of give you guys tips and pointers of areas where you should look. And one of them is to try to go back in time and think about these systems when they were originally installed. How did they work? And in this case, in this plant case, it had constant speed pumps. So we knew there had to be some way of flow control, originally designed. And obviously the things that we saw early on that Mark and the team saw, two pumps running instead of one, okay, the differential pressure not being met. All those things are things that I think that are important takeaways as we talk about the plant, that if you see those, those are all clues and keys if you're getting into an existing building commissioning project that you need to be looking for and get to the bottom of solving. And it was hours of tracing pipes and climbing and testing to find this valve that Mark's talking about. But you're doing sort of forensics here, like, okay, where are we losing the water, type of thing. It's going somewhere. So I just want to share that point of part of what Mark's pointing out is tips to say these are things we saw that were a problem, and that's something you guys should be looking for in your projects is, if you see that DP not met, well, why, where, how is this, if the pumps are moving and the DP is not satisfied, well, something's wrong in between.
And that's exactly right. I mean, you can see here, now we are, in fact, meeting our differential pressure set point. It's a fairly cool day. This was a day of testing, so they would typically be in free cooling, but we've got them operating at a very low 118 tons part load with one 400-ton chiller running here. In this situation, we've permanently isolated chiller 3 here. We've valved it off. So we've abandoned the series counterflow setup here. And we've, as an extra step to this project, we went out and, sought out a mechanical contractor to provide pricing to install automatic isolation valves on chiller 3 here so that we could, in fact, include it in the overall chiller plant control strategy. But that would be something that would happen in the future. So right now, in the picture that you're seeing here, it's just manually isolated, and we're using one 400-ton chiller as our primary stage of mechanical cooling. You can also see here we're not false loading. Up in the top right-hand corner here, we actually added a flow. This is a calculated flow, but it's flow to the air handling units in the penthouse. So in this situation here, we don't need to false load the chiller plant any longer. So there's no flow going to the air handlers here. Also, kind of a side note, we corrected our minimum flow set points here. Prior to this, these were both set at 400 GPM, which could have also been a contributor to our chiller plant just shutting down. 400 GPM is much too low for an 800-ton chiller as a minimum flow. You can still see here, though, on this picture that we are experiencing low delta T, and we provided a recommendation to the owner that they do get a full chilled water system, balancing done to kind of troubleshoot this issue. We were kind of looking at those third floor heat exchangers. Those had a low delta T across them, so potentially this 15-pound differential pressure set point for the third floor heat exchangers is potentially too high and could possibly be lowered. So some results we saw on the air handler side, now that the chiller plant is able to function more efficiently at part load, we no longer need to false load our chillers by locking out economizer mode here. So we've actually set our economizer lockout temp at a fairly high 68 degrees. And you can see we're at an outside air temperature of 51 degrees, perfect economizer weather, and we're very effectively meeting our supply air temperature set point here. 64 degrees, not using any mechanical cooling here. So with the chiller plant controls upgrade, we unintentionally kind of added some new challenges to this project. Now that the chiller plant and the penthouse air handlers are on the Johnson BAS, the remainder of the building remains on the Niagara system, which poses a problem for some of our retro commissioning measures that we recommended. most importantly, static pressure reset. We can't do static pressure reset now because we don't have communication between the VAV boxes and the air handlers in the penthouse. So again, we did some legwork here, and we came up with some options for the owner. Option one is to keep the Niagara BAS and the Johnson BAS separate and just implement the measures that we're able to implement on the Niagara BAS and meet the minimum requirements of the retro commissioning program here. So in this case, we can implement some of these measures here. The downside is that our electrical savings is lower than our target, but we still have a pretty good payback, under a year, not too bad. Big downside though is that the owner is interested in upgrading the rest of this building, and if they decide to do that, they will lose all this programming. So all the effort that went into this programming will just disappear if they do upgrade in the future. So under this option, they'll be left with two separate front ends. So a second option is to upgrade the remaining controllers in the building and go forward and implement all of the retro commissioning measures. So, when coming up with this option, it's kind of thinking about what's best for the owner in this situation, and to make sure that you're giving them some different options here. So we did some legwork. We got went out to Johnson Controls and got pricing from them to do this work. And as you can see here, it's surprisingly a pretty good price. So to go forward with option 2 here, we're able to get our full electrical savings, which is double our target, and we're able to actually still meet the 1.5 years or less payback here. So we're basically getting a full building controls upgrade for under a 1.5 years payback. And a big benefit is that all of the systems in the building will be on one BAS, and it'll be on the BAS that's the campus standard. We can connect this to the campus's extended architecture, and the functionality will be a lot greater. So the outcome of this project is that the owner chose to move forward with a complete building controls upgrade. They had the money to spend, and it was a fairly easy sale. With a payback under a 1.5 years, that's a pretty easy sell. They were able to implement the static pressure reset. They will be able to correct the supply fan speed control, which is critical to making the static pressure reset work properly. The owner will have better control of their occupancy scheduling. It's much easier to adjust on the Johnson system than it is in that Niagara system. And they'll have good reliability throughout the building and improved control. So I think the real takeaway from this project and kind of the lessons learned is to always be looking for the best solution for the owner. Take that extra step to kind of think of all the options that might be out there. Even though it may potentially be outside of your original scope of work, take that extra step and find what's best for the owner, and you'll really end up with a great project. So are there any questions out there?
Mark, it was very interesting in what you had to say. I guess what I find interesting, and there's probably a lot of these companies up in Wisconsin. We have Focus on Energy, which does the same type of thing, I think, as kind of the umbrella firm or whatever to kind of help some of these things along, right? Because you did mention that, was the utility involved with this at all down in ComEd? Did they help you out on this?
Yeah, so the project started as it was a ComEd-based retro commissioning project, so that's how it started.
Okay, thank you.
And Mark, and I'll chime in for a second too. As Mark kind of pulled this together, there's a couple of things I wanted to hopefully the audience kind of take away. Is this started as a utility retro commissioning project, kind of naively, let's get in the building and see some things. So, some of those takeaways are and hopefully you saw that in the slides, some of the things that jumped out, right? So we said before, just, more pumps running than you anticipated, random things shutting down. I mean, these are all the problems that we kind of sifted through and drew out of conversations with the operations staff, differential pressure not being met, low delta T, economizer, set points and lockouts for, economizer mechanical cooling, fans running at 100%. Those are all things that as you go through the screenshot, of the building, looking at the BAS, those are all things to sort of look at that. And it started out as, okay, well, let's kind of get this stuff fixed. And then this project is one that was pretty interesting because it kind of started to wind and twist and go down different directions, from retro commissioning to upgrading the plant, and then we're digging into efficiency curves of what the plant efficiency is and series counterflow, and suddenly we're finding ourselves resequencing the plant and part of the time abandoning what the guys were told to do, which was the series counterflow approach for the lower loads. And then suddenly controls upgrades, and okay, now we're scoping a controls upgrade out with a controls contractor. So you can see on this project, it really sort of, it kind of got off path, then we got it back on, then we got off path again, and we got back on, and it's just one of those of, the way you kind of keep working it with the owner to show, kind of the twists and turns that some of these projects can take.
So we do have some questions here, and John, if you want to jump in. The first question is, we did say that series counterflow is more efficient than using the single chillers in parallel. So why abandon the series counterflow? Well, the answer to that is typically you wouldn't want to. The issue with this plant is that they did have plans for future expansion in the MRI area, which would increase the load on the building. So the plant was sized with that in mind. Unfortunately, that never went forward, and they're left with a plant now that's oversized for the original intent. So they basically have 4 800-ton chillers that can operate independently. However, they're not able to operate at part load as well, and the load just isn't there. At lower temperatures, and we're not talking about that low. We're talking about under 60 degrees. They're ending up false loading their chiller plant. So the solution here was to just abandon the series counterflow, so lose a little bit of efficiency, and then use one of the 400-ton chillers that was originally intended for the series counterflow as the first stage of mechanical cooling. And so what we more than made up for the loss in efficiency by fixing that over-pumping problem, by optimizing the condenser water reset at the cooling towers. So more than made up for it there. I hope that answers that question.
And to chime in too, we've seen this building get handled basically by one chiller. And Mark, you can correct me. I think even up to about a 90-degree day, they only need one chiller. So they only, their peak load is about 800 tons. And they spend a lot of hours, below 70, probably 65 degrees. They only need one of the 400-ton machines. So the way it was valved and piped was if you ran chiller 3 and 5, they were running together, and they would get enabled together. So when you turn them on, it was turning them on basically together. And basically the chilled water would come back to chiller 3 first. So it would take basically the load, it would get the set point, it would then go through chiller 5, and chiller 5 basically said, I have no load, so I'm going to shut down. And after a couple times of cycling on, cycling off, cycling on, cycling off, it would just get into its own like lockout, and it would just say, I'm not going to run anymore. So that was sort of the problem of abandoning it. It's not that we're abandoning the complete approach, but we're saying that, if you're in this spring, fall seasonal weather, just valve it off, disconnect it, and then once you get into the summer, if you want to run series counterflow, you can do that for the efficiency. But for a lot of the year, they're just going to run one of the machines.
So another question we had here was the chiller plant control upgrade price listed in the FIM table? FIM 8 shows $3,500, but the chiller plant upgrade must have been much more than that. That's correct. So as part of the retro commissioning program, you have to keep your payback below a year and a half. So for the chiller plant controls modification measure, so the scope was getting all that programming updated, not the hardware portion of it. So this is just including the programming involved, and the controls contractor estimated that at $3,500. Hardware and everything, I think the price was somewhere around $40,000.
Excellent. Is there any other questions out there, Mark, or is that it?
There's one, not so much a question, but a comment that one of the listeners has experience with series counterflow chillers and has seen pretty poor results. So I don't have a ton of experience with series counterflow, but I would agree with that in general.
And I guess what I would comment is, and I'm not, we can get into a whole nother conversation. I mean, we threw the slide with efficiencies. We're at one condenser temperature. You can start getting into condenser water reset, and the analysis of comparing can get it could be a whole hour seminar itself. So this is a pretty simple one. And as Mark said, and I'll share this, I don't think it was clearly identified. This is what's an MOB. It's a medical office building. It's one of their outbuildings. And the engineers that handle this building also handle a few other outbuildings from the main campus, which is why when Mark said that sometimes they'd have to run back, literally they could be in a whole other building dealing with an issue and the pager goes off. So we were willing to accept a little loss in efficiency by abandoning series counterflow for simply the reliability factor and the operability of keeping the plant running and not driving these engineers crazy. They could be literally unclogging the toilet in one building and get a page that the plant went down in this building, and they're like, okay, I got to run back over there now. So, we concur. Chiller plant efficiencies and analysis is very involved. And we opted in this building to really put a high priority on reliability. And switching back, I had trouble getting on the first part of the call, so I'm going to jump kind of back to a conversation. We were talking a little bit, Dave Gubberud was talking about fundraising and the fundraising campaign that the BCA is putting on. I just recently participated in a Department of Energy panel that was specifically focused on talking about certification. So I'm kind of backtracking just a quick moment here as we're ending our time. But my point of that is the BCA, was invited to the table to talk about certification. The BCA is getting a lot of attention to sort of what we're doing. And it is, the only organization out there that is solely focused on commissioning. So because of that, I think we're in a really good position, and the indicators and what we're hearing from other organizations like ASHRAE, like AIA, are that they would like to see us become a leader in the industry in this certification issue. So this again, just to reinforce what Dave talked about, the fundraising side is, every dollar is important. I think we're at a really important turning point. The BCA, the International Board of Directors, everybody recognizes and said, hey guys, it's now. Like, we need to strike. The iron is hot. Like, it's either step up now, for our organization, or there may not be a now, 5 years from now if we don't hit it. So it's really being viewed. This was not on the radar screen by any of us, a year and a half ago. And at this last leadership conference, this was the, sole focused conversation point, overall above any other priority that the organization has. So it is kind of coming out of left field per se in a little bit, but everyone's really recognizing what an unbelievably high priority this is. So to support that, just again, every dollar counts.
So with that, I guess I'd like to say this webinar stuff is way cool because, between me being in Wisconsin, Mark and Kevin in Chicago, and John, I don't even know where you are in the country.
I'm in Philadelphia at the moment.
Fantastic. It is fantastic when technology works. And I just want to let you know, just as a precursor, next month I'm going to be doing a little presentation on more or less such a simple device as a VAV box, but it's doing just so much more with the use of standby and resets and all that other fun stuff. And then we're going to take a month off in May for our webinar because I think hopefully everyone that's on this call and others will be at the NCBC event that we discussed earlier. Keep looking at the website for updates on that. And in June, we actually have a guest, or not a guest speaker, but somebody other than myself and John and a few others. We actually have Aubrey Swift from DB HMS that's going to kind of give us a little presentation on envelope commissioning, which I think is going to be very interesting. So I do thank all of you for attending. And if you have any questions even after the fact, please send them my way or Mark's way. His email's been up there, and we'll get them answered. We'll do a follow-up next month. So until next month, everyone have a great day at work, and we'll go from there. See you later. Bye.
Thanks, everyone.